Okay, here we go again. Chemistry 3202 course overview. This time we're going to look at Unit 3, Section 2, Lesson 3. We're going to look at heating and cooling curves with respect to enthalpy and a heat change in terms of temperature. And generally these questions, most times they show up on the public exam in one way, shape, or form. And for the most part, it should be an easy calculation. It takes a little bit of time, but I think you guys should be able to do this. So let's have a look at a couple. Okay, this is dealt with on page 651, 652, and there's a few practice items there that you can try as well. And don't forget, now you can check these in the back of your book or in your at the end of the section. And if you can't get them, then fire them off to your online tutor or fire them off into the discussion box and we can see what we can do for you. All right, so here we are. We're looking at this guy here. He's breaking free. All right, at this point I would start singing the song by Queen. I want to break free. I want to break free. All right, that's enough of that. Anyways, we're going to talk about breaking free of bonds and bond formation, because after all, that's what, an enthalpy, endothermic means you're breaking bonds. Okay, and we're also going to talk about strawberries and how we can save our strawberries if we have an impending frost that's coming in the spring or in the fall of the year, depending on whether we want to protect the flowers or the fruit. Okay, so here we go. Here are the outcomes for this section. Okay, what we're looking at here is the idea that phase changes are physical changes. So when we melt ice, it's a phase change. Melting of ice goes to liquid water, all right, and that involves breaking bonds. Phase changes involving vaporizing water to make gaseous water. We're breaking the bonds within the water molecules. We're not breaking covalent bonds, but we're breaking intermolecular forces, those attractive forces. So what we're looking at then is this idea that, how do we identify what's going on if we had to melt something or boil something? So the idea being here, of course, that if we consider melting some ice at 0 degrees Celsius, as the ice melts, it absorbs energy from the surroundings. Obviously, if you have a piece of ice in your hand, the ice begins to melt, your hand gives up its energy. Your hand gets cold, but the ice gets warmer, it begins to melt. All right, so all the energy that's going into trying to melt the ice is going into breaking up the crystalline structure here. We're trying to put enough energy in to overcome the London dispersion dipole-dipole and hydrogen bonding of water. Now what's happening, of course, is as this water is melting, it's gaining energy. It's storing the energy in its bonds. And of course, if we wanted to freeze it, then we would actually release the energy once again. Okay, so of course, the fact that it stays at 0 degrees Celsius when ice melts, or the fact that boiling water stays at 100 degrees Celsius as it boils, is an indication that the kinetic energy is not changing. Because remember, kinetic energy is energy of motion. And as the kinetic energy changes, we see that in a change in temperature. But we don't have a change in temperature because the temperature is not changing. It's staying at 0 as the ice melts, and it'll stay at 0 until every last bit of ice is melted. The water boils at 100. It will stay, the liquid water will stay at 100 till every last bit of water is boiled. So there is no temperature change, therefore there is no change in kinetic energy. So all of this energy that's going in is being stored into the bonds as it melts or as it boils. The temperature does not change. Okay? So in terms of what we're looking at here, if we see energy being stored, we see a gain or a loss of energy. So when we refer to something like plus PE, we're talking about a gain of potential energy. And when we write it as a negative PE, we're talking about a loss of kinetic energy. And likewise, the same thing is true here when we talk about kinetic energy. If we say a plus KE, that means we're gaining kinetic energy. And that's going to be reflective in an increase in temperature, isn't it? The temperature is going to gain as well. I like to write arrow up to say that we're increasing the temperature as the kinetic energy is gained. In the case of potential energy, the change in temperature here is going to be 0. Even though we're adding energy, the temperature is not going up, but because we're gaining PE, the temperature stays constant. It does not change. It stays at 0. So in this case, the delta T would be 0 as well. If we get a negative Ke, then that's referring to a loss of kinetic energy. And of course, that's going to be reflected in a drop in the temperature. So the temperature change is going to be a negative, in which case the temperature now is going to go down, a drop in temperature. Okay? Now, we want to keep this in mind as we start. What's going on here with this? Okay, the temperature is being a little bit hard to get along with there. Okay, so what we're looking at is potential energy. We're not seeing any change in temperature. And if we see a change in kinetic energy, then depending on whether the kinetic energy is going up or down, we're seeing that reflected in the temperature. So that's what we got to keep in mind as we start doing some of these curves. So what we're going to do then is we're going to do a little experiment here. We're going to say, okay, we got a beaker full of ice. Okay, we got a chinch full of ice here. There's no liquid water here. And the beaker is going to start, we got this in the deep freeze, and it's at -10. Okay, so we're at -10. And as soon as we start timing our experiment, we're going to put this over a heat source, and we're going to start recording the temperature. So initially, this is froze solid. Everything's at -10. What I'm going to do then, I'm going to put this in a heat source. Now, we could have used a hot plate, but be more dramatic, we're going to use a Bunsen burner. So here we go. Okay, so the flame is burning there. Heat source like a hot plate would have been better because we could control it and not have it go so fast. But the very first thing that has to happen here now is you're not going to see liquid water right off the bat, because at this temperature, -10, water is still freezing, isn't it? So if this is a gradual heating, not using a Bunsen burner, a gradual heating, what we're going to see is the water, the ice is going to warm up from -10. It's going to go to -9. It's still ice. -8. It's still ice. -5. It's still ice. -2. It's still ice. -1. It's still ice. We still haven't seen any liquid water yet, because we will not see liquid water until we hit 0. So what we see with the graph here is that as we start from -10 to go up to 0, we're going to see this. It's starting as a solid, and at this temperature, we're on the solid side of freezing, all right, because we haven't yet added enough energy to get that ice to melt. So we're -10, -5, we're still solid. At 0, we have solid ice at 0, okay? We continue to heat. What we notice here is that even though we have the Bunsen burner going there and energy is being absorbed, what we're noticing is that the ice is just starting to melt. So some of the ice is starting to disappear, and we can see that the beaker is starting to fill up with ice. And we're going to stir this so that we can uniformly distribute the heat. And what we're noticing is that, hey, the temperature is not changing. As we continue to read this temperature, the temperature goes up from -10 to 0, but it stops. That's where it stays. It doesn't move any further. Because what we're trying to do is melt the ice. All the energy is going into the ice. All right, if we continue to heat this, it's going to take a fair amount of time because there's a fair bit of ice there, and it takes quite a bit of energy to break up these bonds. So as the ice begins to melt, okay, the temperature stays the same, and the ice is beginning, this magic ice is not floating, eh? But you get the idea. As we continue to melt this ice, the level of the water starts to go up, but the temperature stays the same. The temperature did not increase. It stays the same, staying at 0. And as we continue to heat it, it stays the same. We're stirring it up. The ice is beginning to melt. The level of the water starts to go up here because we're making more and more liquid water. And all of this liquid water is at 0 degrees Celsius. Eventually, as this last ice crystal, okay, let's float it to the top here. As this last ice crystal begins to melt, we're still at 0, aren't we? Because any energy that's going into this water is going into breaking up that ice crystal. None of the molecules have got excited yet. So what we have here is a change from solid ice to liquid water, but everything is still at 0 degrees Celsius. Because any energy that's going in is going into disrupting the very last ice crystal that's left. Okay, all of a sudden, the last ice crystal, enough energy has been added, the last ice crystal goes, poop, it disappears, and now all of a sudden, there's nowhere else to store energy. All of the ice crystals have stored as much energy as they can. They've all broken up. They're gone. There's nowhere else to store energy. What happens here now is as we continue to heat, the level of the temperature starts to rise because these liquid water molecules now that are at 0 begin to get excited. So what we see here is the curve begins to rise once again. So the temperature goes up, liquid water at 0, liquid water at 5, liquid water at 10, liquid water at 50, liquid water at 70, liquid water at 80, liquid water at 90, liquid water at 99 degrees Celsius, still liquid. None of it is boiled yet because it doesn't have enough energy. All of a sudden we hit that magic number again, the boiling point of water here, 100 degrees Celsius. So at this stage, we're on the liquid side of 100 degrees Celsius. The water has not yet boiled. We continue to heat it. All of a sudden the water says, well, I can't get any hotter. I'm as hot as I can get. I'm only allowed to be 100 degrees Celsius. So what happens here now is it's got to store the energy somewhere. So what happens is we start to see some vapor forming over this bottle. Okay, the water starts to vaporize. Now this is not a good experiment because we have a closed system here, and this is probably going to explode if we build up the pressure too much. So we'd have to somehow vent this, let the gas escape, right? So we would vent this. And eventually what happens here, of course, as the water begins to gain energy, the energy is going into vaporizing the water. The temperature no longer changes. The temperature goes up to 100 degrees Celsius, and that's where it stops. It doesn't get any hotter. Because all of that excess energy, remember the liquid water molecules are going as fast as they can at 100 degrees. The extra energy that's being added is being stored when we break the bonds to vaporize it. So as we continue to vaporize and vaporize, what happens is more and more of the vapor escapes from the container. The liquid volume starts to go down. Okay, the temperature still stays at 100, assuming the thermometer is still in the water here, right to the bottom. And eventually all of the water begins to vaporize and boil till all of a sudden, just like the ice, all the liquid water now has been vaporized. It's been turned into gas. It's all been escaped out through the container. Any gas that remains in the container now is going to start to get real excited. So we're at this stage of the game now. We've got gaseous water at 100 degrees Celsius. Any more heat we put in there, now the gas molecules are saying, boys, we got nowhere else to store this energy. All the liquid's gone. We've got no more storage left. So what happens now is the gas molecules have no other choice but to get excited. And as the gas molecules get excited, the temperature begins to shoot up again. The gas molecules are moving faster and faster and faster and faster and faster, and that's reflected in the larger and larger and larger temperature. So we can see then that we're going from a solid to a liquid to a gas. And what's happening here is we're seeing a phase change occurring where we have no temperature change. So let's see if we can't see what's going on here in terms of a potential energy and a kinetic energy gain. All right, we said at this stage of the game right here, the very first stage, I'll call that stage 1, what we're seeing is an increase in temperature. Aren't we? The temperature is going from minus 10 to 0. So the temperature is increasing in that section of the graph. So what we're seeing then is that if temperature is increasing, then the kinetic energy must be going up. But if all the energy is going into making the molecules move faster, that means we're not storing any energy. So the change in potential energy is going to be 0. Because all of that energy is going into getting the solid molecules excited. We're going faster and faster and faster and faster, and that's reflected in the temperature. None of the energy is being stored. All of a sudden we reach the point where the solid crystals can no longer move any faster, and now the energy is being stored. So what we're seeing at this stage right here is that the change in temperature is 0, which means the change in kinetic energy is 0. Well, where's the energy going? Well, we're seeing a gain in potential energy at this stage of the graph right here. Okay? So in that phase, we're seeing a gain in potential. The temperature is not changing, but there's energy going in. It's being stored. The next phase of the graph, once again, we're seeing the liquid molecules getting all excited here now. They're getting faster and faster and faster and faster, but the energy is not being stored. So we're seeing an increase in temperature here, which means we have a gain in kinetic energy. However, that energy is all going into making the water molecules move faster. None of it is being stored. We're not at the stage where we can store it anymore. So what's happening is the potential energy change is 0. We're not gaining any more potential. And when we look at the next phase of the graph, all right, we're seeing that once we reach that 100-degree mark, now the liquid molecules are moving as fast as they can. Any extra energy has to be stored. So at this stage of the graph, we're seeing a change in temperature equal to 0, which means the change in kinetic energy is equal to 0. But that extra energy is gain of is being stored. Gain in potential energy. Let me just move that over a bit so we don't confuse it with the other portion. There we go. And of course, at the last region of the graph here, we're seeing that, okay, all of a sudden all our energy has been stored, and now all of these gas molecules are getting more and more excited, going faster and faster and faster and faster. And that's because the temperature is going up, and that means we're gaining kinetic energy here, which means now we can't store any more potential. The change in potential is 0. So we're seeing two distinct things happening in the graph. Either the temperature is changing or it's not. So we've got 5 distinct regions where we got 5 different things going on. So for instance, in this part of the graph right here, we're seeing fusion happening. Not fusion, fusion. Here we go, fusion. And we know what kind of calculation we can do there for fusion. In this region of the graph, we got vaporization happening. And we can do a specific calculation for the enthalpy of vaporization. So we got 5 distinct regions here with 5 distinct calculations. If we want to figure out how much energy we just put into this, then we have to do 5 distinct calculations. So we're looking at this, and we're saying in the horizontal regions of the graph, there's no change in temperature, so therefore there's no change in Ke. That's what we were doing right here, right? In the horizontal regions, there's no change in temperature, so there's no change in Ke. The added energy is being stored as Pe. Okay, so there we go. The diagonal regions are the regions where we're seeing an increase in kinetic energy, because this is where we see the change in temperature. And I'll leave that down there, I guess. What I'll do is I'll put two boxes around that, and we'll just put her like that and like this. Okay, and there we go. So we want to be able to see what's going on here with these calculations. So let's go have a look at some of the calculations. So when do we use each calculation? Because we know we've got a change in temperature in one situation, and we got another situation where there's no change in temperature. So where would we use Q equals N delta H? Well, in the horizontal regions, the regions where there's no temperature change. And it depends on what the state of matter is and what the phase change is, so whether it's fusion, vaporization, solidification, condensation, depending what direction we're going in. So we'd have to be able to decide what the process is. And the sign of delta H depends on whether we're heating it, plus delta H, or whether we're cooling, the energy is being released, that would be a negative. And there we go. And therefore, if we look at Q equals MC delta T, this would be situations where it's a diagonal line, where there's a change in temperature. And what we have to watch out for here is the specific heat capacity, C, depends on the state of matter. Remember, it's different for solids, liquids, and gases. So you'd have to be able to figure out from your chart, or your table, your graph, whether or not you're heating up a liquid, or whether you're heating solid, or whether you're heating gas, because the value of C is going to depend on what the state of matter is. All right? And finally, we notice that the change in temperature is going to be different for each diagonal region. All right? Let me just show you what I'm talking about. The very first diagonal region only goes from -10 to 0. So the first region is only heating 10 degrees. So the change in temperature is only 10 degrees. Whereas region number 3 here, region number 3, is showing me it going from 0 to 100. So this is reflective of a 100-degree temperature change. And in this case here, we only heated it up to 110, so we're seeing it going from 100 to 110. So each region would have its own distinct temperature change, as well as the fact that we're dealing with solid down here, liquid here, and gas here. So we'd have to take all that into account. So there's a little bit here to keep in mind as we do this. So let's try an example. Let's do the exact same heating here now. We're just going to do a graphical analysis here. So we're looking at this and we're saying, okay, let's take 100 grams of ice, so we know exactly how much ice we're going to heat up. And we're going to start at -10, and we're going to turn it into steam at 110. So we're looking at our graph and we're saying, okay, we're going to start at -10. We're going to end at 110. And we know that we're dealing with water, so we're dealing with a melting point of 0 and a boiling point of 100. So our graph would start going like this. We're going to start heating it up till it gets to 0. It begins to melt. And then it all melts, of course. And then, of course, as it all melts to liquid water, then it begins to heat up, as we just did on that other graph there. And as it heats up to 100, it's going to start to boil. There we go. We level off again. And when all the water is boiled, what happens then is the steam begins to warm up. So we're dealing with 5 distinct regions on this graph. Okay? And in region 1, because it's a temperature change, we're going to do Q equals mc delta T for ice with a 10-degree temperature change. In region 2 here, because it's a horizontal region, it's a phase change where we're melting the ice. It's fusion. So the calculation is going to be Q equals NH fusion. In region 3, we're dealing with liquid water with a temperature change. So Q3 is going to be mc delta T, using the C value for liquid water. And the temperature change this time is 100. Q4, again, is a phase change. It's vaporization. So this guy's going to be NH vap for the vaporization of water. And then the 5th region of this curve is going to be the heating up of steam. So Q equals mc delta T for gaseous water. And the temperature change is 10 degrees. Now, one of the things people like to do here is this is wrong. Let me just show you what people like to do here. People like to look at this and say, okay, we're heating this from, they don't talk like that obviously, but we're heating this from -10 to 110, so they simply do one curve like that. And then they try to do one calculation, because look what's given. You're given a mass, you're given a TI, you're given a TF. We know we're dealing with water, so we can use the specific heat of water. That's one calculation. Q equals mc delta T. On the public exam, if they ask you to do this question, this would be worth 3 or 4 marks. Do you honestly think they're going to give you 3 marks for doing one simple little calculation? Not a chance. If you're going to get 3 marks, you have to do 3 different things or more. All right? So in this case, looking at this problem, we're saying, yeah, well, that's obviously not going to be the case, because we got to do at least 3 or 4 different things to get 3 marks. So don't fall into that trap. Okay? And again, down on the bottom here, this is going to be time. Okay, so let's do the calculations then. I'm going to go to another page to do the calculations, and it's a lot of work. We got to do 5 different calculations, and then we have to add them all up to get the total energy for the full phase change. So here we go. This is the calculations. The very first calculation we said for region 1, Q equals mc delta T. It's 100 grams. Here's the specific heat of solid water, ice. And the initial temperature is -10, so TF minus TI, so 0 minus 10, which is a 10-degree temperature change. Works out to be 2,010 joules. Now, here's an important little trick you got to watch. We got to have the same unit for each of these calculations, so it's a good idea to change everything to kilojoules. So in order to change joules to kilojoules, you divide by 1,000. So it's going to be 2.01 kilojoules. Okay, stage 2 of this graph is the phase change. So this is going to be Q2 equals N delta H fusion, so that depends on the number of moles. So mass over molar mass of water times the heat of fusion plus, works out to be plus 33.41 kilojoules. So we're in business here. We've got the same unit. Stage 3 here, again, is the heating of water. So that's going to be Q equals mc delta T for liquid water. 100 grams times 4.184 is the heat capacity of liquid water. See how that's different than the heat capacity of solid water? Big difference, eh? Okay, so don't mix that up. The temperature change here, TF minus TI. Well, for this heating of water, for stage 3, this is where we start heating the liquid water. Liquid water starts at 0. It ends at 100. Okay, so the difference in temperature is a 100-degree change, which is a gain because we're going up. This works up to be 41,840 joules, which is 41.84 kilojoules. And again, we've got the same unit here, so we're in business. Stage 4 was the vaporization of the water. We're starting to boil it. This is the heat of vaporization. Again, it depends on the number of moles, mass over molar mass of water. And this value is given, of course, so it works out to be 226.42 kilojoules. Every one of these values is positive, of course, because we're gaining energy. We're heating it up. And last but not least is the heating up of the steam. So in stage 5, we created steam that went up 10 degrees. So M equals mc delta T, 100 grams of steam. Look at the specific heat of steam. It's different than liquid water, isn't it? Big difference. So it's going to affect your results. And the steam heats up. We don't get steam until we get 100 degrees Celsius, do we? So the change in temperature for the steam is going from 100 to 110. That's only a 10-degree difference. Okay? So we calculate that in there. It works out to be a plus 2,010 joules, so we change that to kilojoules, or again, divide by 1,000, and you get a plus 2010. What we have to do here now is add everything together. So Q total is going to be Q1 plus Q2 plus Q3 plus Q4 plus Q5. And because we have everything in their correct units here, kilojoules, 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 we can safely add these guys up, and we get 306 kilojoules. It's a lot of energy. Now, upon inspection of these numbers, look what's taking the most energy. For heating up solid ice from 10 degrees is only 2 kilojoules. In order to boil that same amount of water, it's absorbing 33 kilojoules. That's a lot of energy when you compare it. And look, when you're warming it up from 0 to 100, you're warming it up 41 kilojoules. That's a lot of energy. But look how much energy it takes to boil that same amount of water. Phenomenal amount of energy being stored in the bonds. So those London dispersion dipole-dipole and hydrogen bonding forces are quite strong here, and that's reflective, of course, of the energy that's required to pull them apart. Okay? So looking at this, the energy of vaporization makes up the lion's share of the energy change. So there's a significant amount of energy that goes into disrupting that. So that's a lot of work. Now, I don't think they would give you a complete going from ice to gas on the public exam. They would probably say ice at -10 going to liquid water at 50. So on the public exam, they probably stop you about right here. Okay? In which case you would heat it up to 50. So in that case, you're going from -10 to say about 50 degrees, so you only got 3 zones that you have to calculate. All right? Or they might say, you know, let's take liquid water at 20 and create steam at 110. So in that case, you got 1 phase change. So in that case, 3 calculations, 3 marks. That's a good idea, all right? So be careful about the phase changes. Now, we don't always have to use water. Lots of times, a lot of people think that melting points and boiling points are always going to be 0 and 100. Yeah, that's true for water, but what if we have some other substance? So here's an example where we're going to take some chlorine gas, and we're going to take 10 grams of chlorine gas, and we're going to start it at -40, and we're going to cool it down to -130. Wow. We're already cold. We're getting colder. So we want to sketch the cooling curve for this, and we want to be able to calculate the energy that's involved in this phase change. So when we look at this, we're saying, okay, here's 0. We're starting at -40. We're cooling it down to 130. If we look at the boiling point and melting point of chlorine, it boils at -346 right there. Well, we're not even up there, are we? At this page, at that stage right there, that's where the chlorine is actually going to turn into a gas. So anything above 34.6, it's a gas. Anything below 34.6, it's going to be a liquid. So at -40, we're in the liquid state, are we not? Right? Because at -34.6, we'd start to boil, i.e. turn into the gas. So we're going to start cooling this down. And as we cool it down, it begins to cool, cool, cool until it hits a -101. At -101, it's the melting point, or the reverse of melting is freezing. So it begins to freeze. It stays at -101 until every last bit of the chlorine is solidified. Once everything solidifies, then it turns into the solid, right? So what we have here is the liquid form of chlorine undergoing a change in temperature. Okay? So we got liquid chlorine there. What happens here is the phase change. We're seeing fusion of chlorine. That's not fusion of water. Fusion of water occurs at 100. That's the fusion of chlorine. So Q2 is going to be N delta H of fusion for chlorine, and that value was given to us up here, fusion of chlorine, 320. And then finally in step 3 here, in the third region of the graph, we're seeing the solidification of chlorine. It's solid, and what's happening here now is the solid is getting colder and colder and colder and colder and colder and colder and colder. So we're seeing the MC delta T for solid chlorine. And you notice up here they give us the value for liquid and solid chlorine. Okay, 3 calculations. In this case we're cooling, so energy is being released as it cools. Every one of these calculations is going to be negative. So the first calculation, Q equals MC delta T for the liquid, 10 grams. This is the specific heat capacity of liquid chlorine that's given to you. All right? No, it's not like water because it's a different species. It's a different substance. It has a different value. And the cooling is going from minus 101 to 34.6. What did I do there? See what I made a mistake. It's going from minus, the final temperature for this stage right here is minus 101, and it's going from 40. So I got this calculation wrong. So let me just fix that. Okay. So it's going from minus 101, and the initial temperature was minus 40, which means now I have to do my calculation all over. So let me calculate this. 10 times 0.480 times minus 40. It works out to be 292.8, negative 292.8. So let me fix that. Okay, negative 292.8 kilojoules. Okay, actually joules. Joules, joules, joules. And we know it's going to be joules here because the unit for specific heat capacity is joules per gram degree Celsius, so this is joules. So remember now, I always want to convert this to kilojoules. And I'm going to divide by 1,000, so this is going to equal 0.2928 kilojoules. Not very much energy, is it? Chlorine doesn't have as many bonds. You know, the London dispersion forces, doesn't have dipole-dipole, doesn't have hydrogen bonding, so the forces of attraction are not that strong here. So what we see here happening now in Q2, this is going to be the fusion of the chlorine from liquid. It's going to fuse to a solid. So we see Q2 is N negative delta H fusion, so it's 10 grams divided by the molar mass of chlorine. Don't forget chlorine is Cl2, so 2 times chlorine. This is the heat of fusion for chlorine. Notice how it's different than water because it's not water, it's chlorine. And we do our calculation here, we get a negative 4.513 kilojoules. Not a very big number, is it? And again, that's because chlorine only has London dispersion forces. It's nonpolar. It's got no dipole-dipole. It cannot hydrogen bond, so its forces are very weak. And that's reflective of that temperature. Q3 here, of course, is going to be the third region of this graph. And this is where we're going from starting to be a solid, and then the solid is cooling, cooling, cooling. So this is the temperature change of the chlorine. It's going from TF, which is minus 130, to a TI where it started to be a solid at minus 101. So here we go. This works out to be negative 60.9. You notice here the specific heat capacity of solid chlorine. It's different than liquid chlorine because it's behaving differently. It has a different heat capacity. Okay, we add these numbers together, and obviously I got my first one wrong. That's supposed to be 0.29 kilojoules. 2928 kilojoules. And again, in this third equation here, you're given joules per gram degree Celsius, so don't forget to change it to kilojoules, right? Divide by 1,000. We're going to add these numbers up, and clearly I've got this wrong now because I messed up on my temperature. Easy to make mistakes here. That's why you got to write things down. Okay, 2928 plus a negative 4513 plus a negative 0.069. And I get a negative 0.813. That's weird. That one works out to be 831. Weird. All right, negative 8.13. And you notice that with number one, we don't have a lot of chlorine here. We're only dealing with 10 grams. And number two, the phase change doesn't take as much energy as water because it has weaker forces of attraction than water. And there we go. So again, be careful with the temperature differences. You notice how I made a mistake here. I had 34.6 on my graph, and that's what I used, but remember we cooled it starting at minus 40. Everything is cooling. We're losing energy. Energy is cooling here. The molecules are slowing down. They're getting cooler. Down here, the molecules are solidifying, so that energy of the liquid is being released. The potential energy is being lost. We're losing potential energy as we form this solid chlorine. There we go. Okay, here's another one. This one's dragging on, I know. This is a different substance known as ammonium chloride, and this is actually showing a phase change of sublimation. So sublimation is where it goes from a solid to a gas. The reverse of sublimation would be deposition. So we want to do a heating curve this time for some solid ammonium chloride that's going to be heated from 25 to 300 degrees Celsius. Now what we got to watch out for here is the temperature of sublimation. We know it occurs at 200 degrees Celsius. So we're starting at 25, we're ending at 300. So we're going through that phase change, and that's what we have to keep in mind here. So when we do our graph, we have to keep in mind that even though we're starting at 25 and we're ending at 300, we're going through a phase change. So below this, we're going to be a solid. Above that, we're going to be a gas. So our graph is going to have three regions, right? We're going to heat it up. The solid gets excited, more excited, more excited. All of a sudden, it gets to the point where the energy starts to be stored. It changes to the gas phase. It skips the liquid phase. That's what sublimation is all about. And then once all the gas is produced, and the gas gets excited and the temperature goes up. So again, we've got three distinct calculations. Q equals mc delta T for solid there. We got Q delta equals NH sublimation there. And in this case, we've got Q equals mc delta T because there's a temperature change for the gas. So our three calculations, Q1, Q equals mc delta T for the solid ammonium chloride. The temperature change Ti is minus 25, so Tf minus Ti, so 200 minus 25. You notice we don't go through the entire right up to 300. We go to 200, we stop. That's the energy change for the solid. All right. Again, it's joules per gram degree Celsius, so don't forget to change to kilojoules. Stage 2 here is showing us the heat of sublimation, which is going to be the number of moles, which is mass over molar mass of ammonium chloride. And this is a gain of energy, right? Positive. And that works out. Okay, and then in phase 3, we're looking at the heating of gaseous ammonium chloride. And in this case, it's mc delta T because the gas goes up from 200. That's where we're starting. That's my initial temperature for the gas. And my final temperature of the gas is 300. So my temperature change, Tf minus Ti. 300 is where we stop. 200 is where we started heating the gas. And again, joules here. So I have to change my answer to kilojoules, right? And then we add these all together. They're all positive because it's a gain of energy. So Q total is a plus 4.6 kilojoules. Now once again, you notice that this value is not as large as water. The sublimation of ammonium chloride does not involve as many strong forces as the vaporization of water. Okay? It's a little less than actually the fusion of water. So you can see that you can put these guys in relative terms in terms of how strongly the ammonium chloride is being held together in a solid state. All right, it's a reflection of how strong these bonds are, this value. There we go. Okay, so again, be aware that not always do we ask you to do a heating curve for water. Different substances have different critical temperatures. All right, it's not always 0 and 100. That's for water. Different substances have different boiling points and melting points. Okay, here's a couple questions then. It says, why does the molar heat of vaporization for a substance always seem to be greater than its molar heat of fusion? And the reason for that is it's got to do with the energy that's stored in the bonds. And generally what's happening is the molar heats of vaporizations are generally higher, indicating that the bonds are stronger amongst the liquids than they would be amongst the solids. All right, and that's true in almost all cases, that the liquid, because of its interactions, that it tends to be, the molecules of the liquid tend to be closer together than they would be in the solid. And we know, just like magnets, the closer they come together, the stronger their forces get. So in the case of the liquid phase for water, the molecules of liquid water are closer together, the attractive forces are much stronger. In the case of solid water, remember as solid water forms, it creates an air pocket in the middle. And that's why ice floats to the surface. So because of that air pocket, the molecules of water tend to push apart a little bit. Okay, number 2 here. Which event should cause a more severe burn? Condensation of 10 grams of steam on your skin, or the cooling of 10 grams of water from 100 to 37. Now 37 is body temperature. 100 degrees Celsius is the temperature that the water is boiling at. So this is the old trick that people do. They sometimes, magicians like to do this. You put your hand over steam, you get a severe burn. But you can plunge your hand in the boiling water and it doesn't hurt for the most part. Don't keep it in the boiling water, just plunge it. I wouldn't recommend you do any of it. So which would cause a more severe burn? And what we're looking at here is we got to look at what's going on in each situation. So in the first case, where we're simply plunging our hand in the water, you're simply getting liquid water on your skin, and the liquid water at 100 degrees Celsius, it has to cool down to liquid water at 37 degrees Celsius. That's body temperature. So we could easily calculate that energy. Q equals mc delta T. It's simply the cooling of liquid water. In the case of steam, if we get steam on our skin, that what has to happen first is the steam is a very, very high energy. So all that stored energy that's in the steam has a great deal of potential energy. All that energy has to first be released into your skin as the steam condenses to form a liquid. Once the steam condenses to form a liquid, then you still have to release that energy to cool it down to body temperature. So it's like a double whammy. In this case, you get a severe burn from the cooling of the liquid water. In this case, you get an ultra-severe burn because the vaporization of water involves a tremendous amount of energy compared to this. So you get an extremely severe burn because of condensation of the steam, and then you would get another double burn here, or an extra burn, because of the cooling of the water. So because of that phase change, there's a tremendous amount of energy involved. Okay, and this is why on aircraft carriers and things like that, they use a steam catapult to throw the aircrafts off the deck of the aircraft carrier. You see all the technicians and whatnot that are working on the steam catapult. They generally have their faces and everything covered with like an asbestos type material. Everything is covered. They got goggles on. Every bit of flesh is covered because that steam that's coming out of the catapult is at thousands of degrees Celsius. Imagine if they got that on their skin. They'd have to cool the steam down from, say, 1,000 degrees Celsius down to 100 degrees Celsius. That would be a tremendous burn. And then all that steam has to condense on their skin, and then it would have to cool down to body temperature. So a severe burn would be resulting. So that's why they cover all their exposed flesh. There we go. Okay, same sort of thing happens here. If you're lost in the woods in the middle of the winter, these have been known to be public exam questions, by the way. If you've been lost in the woods and you become thirsty, would it be better to drink water from a running stream, or would it be better to pick up a chunk of ice or snow and begin to nibble on the ice or snow? And what we want to look at here is the idea is the same sort of thing as the steam scenario. Even if it's minus 20 outside, liquid water is going to be above 0 degrees Celsius. So no matter, it might be minus 20 outside. If I see a river flowing, that water is 0 degrees Celsius. If it's going to be below 0, then it's going to be solid. It's going to freeze, right? So anything that's liquid is going to be above 0 degrees Celsius. So if we drink that, all we have to do is warm the liquid water up from 0 to 37. That's not too bad because warming of water doesn't take a whole lot of energy, right? It's a liquid. If we had to nibble on a chunk of ice, what's going to happen here is if that ice is at minus 10 or 20, because that's what it's going to be, if the surrounding temperature outside is minus 10, then that's going to be the temperature of the ice. The very first thing you have to do is warm the ice up from minus 10 to 0. Then we have to melt the ice in our stomach, and then all that cold water has to be warmed up to body temperature. That's a lot of energy changes going on here. This fact that we have a phase change, that takes a tremendous amount of energy, and therefore we could probably put ourselves into hypothermia based on the first law of thermodynamics. If we have to put all this energy into to heat up the ice and then melt the ice and then warm up the water, that energy's got to come from our body, and therefore we can put ourselves at risk of hypothermia because that energy is going to be lost from our internal core. So never eat solid ice. I always try to get liquid water. Okay. Number 4 here, why do strawberry farmers spray their crops with a fine mist of water when there's a risk of frost? All right, same sort of principle. What we want to do here is we want to spray this mist. We want to vaporize the water and get it into the air. We want to create a fog around the strawberry plants. And when we create a fog, as the temperature outside begins to cool, Rather than the strawberries freezing, what has to happen is the mist that's in the air first has to solidify, and it starts to freeze on the surface of the strawberry. And that creates a barrier, and it kind of insulates the strawberry itself. And then, of course, that whole thing has to cool down to -2. So this process here of solidifying the mist actually releases energy. Energy is being released as the liquid water freezes. Where's that energy going? Into the strawberry to keep it warm. So it's kind of heating up the strawberry a little bit. It absorbs it and keeps it from freezing. There we go. We do the same sort of thing in greenhouses. If you ever have a greenhouse, we do the same sort of thing. We like to get a lot of water vapor in the air. So during the day, a lot of humidity builds up in the greenhouse. Before the sun sets, it's important to close up all your vents and your doors and all your windows so that none of this humidity can escape. And nighttime, when the sun goes down and it begins to cool, all this humidity begins to condense. And there's a tremendous amount of energy in the vapor. And as that vapor condenses, all this energy then gets released into the greenhouse, keeping the greenhouse nice and warm during the night cold air. And it prevents frost from getting at your tomatoes and whatnot. And it's pretty neat. It works. All right, but you've got to trap that humidity inside the greenhouse before the sun sets. And there we go. All right. Very long lesson. I'm sorry for keeping you so long, but again, check out some of these guys. Definitely one of these on your public exam. Usually it's a 3-stage curve. They may give you water, they may give you something else, but be aware of the different phases. Okay, so double check some of these. Try some of these out. There's a couple done in your textbook as well on these pages right here. Right, a few sample problems given there. Give them a try. Make sure you know how to do them because, again, it's going to be on your public exam. And lots of examples here. Go look at a couple public exams. Pick out the questions that deal with heating curves and give them a try. All right. See ya. Have a great day. Bye-bye.